So now we've done our linear elasticity model and we're trying to interpret the results and visualize them. And it's difficult because the strain and the stress are matrices and we can't really visualize those very cleanly. So what I wanted to do now is discuss different ways to break up those matrices and interpret those results and visualize those results. We need to do a little bit of math to set the stage and then we'll move into COMSOL and see how it's being presented. So the way that strain works is that we're taking an initial volume, V naught, and then deforming it through this strain, epsilon, into some shape that is potentially a different area, a different volume, different size, as well as a shear. Okay. Now, the way that we just described that turns out to be both conceptually and mathematically conceivable. In other words, we can split up the transformation into an increase in size followed by a shear. Okay, so we move from V naught to V, and then we preserve our volume and we shear this thing into our final configuration. This size increase is called a homogeneous strain. And it's homogeneous because every point in this material is increasing in size together. Then you have something called the shear strain, or the deviator is the terminology that we're going to use and COMSOL uses, and that is volume preserving. So there's no volume change between here and here. In linear, small, infinitesimal elasticity, it turns out that these transformations are additive. You can actually do one plus the effect on the other one. In finite strain and large deformation calculations, they're not additive. They have to be multiplicatively decomposed. Let's look at some of the mathematics here. We've got epsilon is the sum of these two terms. And what we're going to define is a scalar field called the volumetric dilation. In this case, delta, I know, delta usually change, we ran out of letters, right? Delta is nonetheless defined as the difference in volume over the initial volume, and it turns out that this is the trace of our strain matrix. Trace is one of these matrix operations. What we're doing is we're summing the diagonal, okay? And that's going to give us the amount of increase in scale, area, volume, size that this matrix is describing. If we did want to recover the original homogeneous strain, what we would do is just multiply delta over 3 by our identity matrix, right? 1, 1, 1 along the diagonal. And lo and behold, we get this. The reason why 3 is because we're in three-dimensional space. Okay, we can then use that to define what's called the strain deviator. And the strain deviator, again, this entire matrix, you can show that it is volume conserving. So if you try to take the trace of this, you would have to find that that trace is 0 necessarily. Okay, turns out we can do the same thing with stress, and this is particularly useful. For historical reasons, this scalar variable that describes our homogeneous part is identically the pressure. Okay, the only problem with that is that stress is defined as being positive when it's pushing out. Pressure is being defined by convention to be positive when it's pushing in. We're under pressure, right? No, 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 no. I love that song. So when we define it, we use the trace and we have the negative 1 over 3, again, three-dimensional space. Off we go. And we can define our homogeneous strain tensor as now negative P times our identity matrix. You just kind of have to be aware of that negative floating around. Okay. When we do this decomposition, we get our stress deviator, right? Simple enough. Just to put this into context, fluids, generally speaking, unless you're into special fluids called viscoelastic or elastoplastic ones, cannot support a stress deviator. Stress deviator is the shear. And if you try and shear a fluid, it's just going to float. It's just going to slip. Therefore, you will not have shear stress on a fluid, but you might have homogeneous stress. Your fluid could be under pressure, right? I won't do the song again, don't worry. So one of the ways that you can visualize the effect of the strain is, the effect of the stress is through the pressure. There's a problem with that though that I'll talk about in a second. Now, when we talk about elasticity, right, elasticity will only take you so far before your material yields, and then you are no longer in your elastic domain, now you're into your plastic domain. People like me would call that plastic flow. Hint, hint, nudge, nudge. There's an overlap with laminar flow here. Don't worry about that for this course. Okay. So there's a criterion for yielding called the von Mises stress criterion. The von Mises stress is a way to measure the magnitude of our shear stresses. So what we have to do is measure the magnitude of our stress deviator. Now, if we were considering a vector, everybody should know how to measure the magnitude of a vector, right? You dig up Pythagoras, you ask him to teach him his theorem again, right? You take the square root of each element in that vector squared, sum them together, you take the square root of all that thing, and you get the length of your vector. Turns out you can do the same sort of idea with a matrix. It's called a matrix norm, and it's not unique. There are a whole bunch of different matrix norms. But the idea for this one is basically the same. You take every single element in your matrix, square it, sum that, multiply through by this magic factor, and you get the von Mises stress. Here it is in its element-wise beauty. Right, that's with the stress, the homogeneous stress already subtracted. You can calculate that, no problem. The nice thing about this is that it gives you an idea of the maximal amount of shear stress that your material is under. So when we go to our COMSOL, this is the bracket example that we're going to be talking about soon in tutorial. What you're going to see here is when you add in your linear elastic material, right, you select your domains, you input some of your material properties, and then there's a magic field here called using mixed formulations. Okay, what this addresses is cases where your materials could either be very, very hard and they're basically incompressible or nearly incompressible, or the opposite end of the spectrum, they're very soft and they could actually compress very easily. So like a sponge or something like that versus something that's very hard and won't let you compress that. It turns out that numerically, right, both of those cases are different extremes of the volumetric effect of the stresses. Okay, for when you're solving this numerically, that causes a lot of problems with the solver. So the mixed formulations create another variable solving specifically for the elastic dilation, the volume dilation, or the pressure as the homogeneous stress. And then by calculating for that separately, it numerically makes a lot more sense. It doesn't make more sense. It is more numerically stable. Okay, geometric nonlinearity, by the way, we spoke about. Here it is showing up here. Strain decomposition, again, for linear small elasticity, we can assume additive. In general, it would be multiplicative, but you don't have to worry about that for this course. Okay, when you go to visualize your results, so first of all, what you're generally going to be looking at, what COMSOL is going to suggest naturally, is your von Mises stress. This is at the Gauss points. That's a finite element method. That's numerical methods. Don't worry about that, right? The important part here is that this is your von Mises stress, and that's what you're seeing here. That is the maximal amount of shear that you're subjecting your material to. Whenever you make these plots, by the way, as a quick aside, you now have the option, you did before, but you didn't have any use for it. If you right-click on that, you can get a subnode for deformation. Okay, deformation literally just deforms your domain when you're viewing it. COMSOL is smart enough to realize that you're solving for a displacement variable and automatically populate that in there, which is nice. But pitfall, right? It's going to automatically assign a scaling variable here. That scaling factor. Okay, strains and displacements are generally speaking small, hence infinitesimal strain. So if this is just 1, when you go to plot it, there is a little bit of a displacement here, but it's too small for you to see. So in order to actually visualize anything, you have to let it scale it, and then it makes it bigger. The pitfall here is if you go back and you change some of your conditions and you replot. So if you reduce the amount of stress your material is under and you replot, it's going to look exactly the same. And you're going to be scratching your head about, well, wait a second, what's going wrong here? Turns out that the answer is actually your scaling factor, right? COMSOL has automatically scaled it back to exactly what you saw before. So just be aware of that. Keep that one in the back of your mind. Okay, coming back to here though, quickly, we have the expression, so we can look at the von Mises stress, or another one that's common is the pressure. The problem with the pressure is, well, let me go back to the other one. Okay, this von Mises stress, because it's measuring the shear, it doesn't care about, for example, the atmospheric pressure, the ambient pressure that this material is subject to. So if you took this bracket and you did it on the surface of the Earth, or you did it at the bottom of the Mariana Trench, or you did it on the moon, you would have the exact same result. Okay? Your pressure, though, is going to change, because that reflects your ambient surrounding pressures. That's why they're kind of separate. That's why pressure is kind of devalued compared to von Mises for certain applications.